Hello and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 5, Geometric Figures, Lesson 3, Can You Say It with Symbols? Starting with the Ready section. Remember when you write a congruent statement, such as triangle ABC is congruent to triangle FGH, the corresponding parts of the two triangles must be the parts that are congruent. For instance, from the congruent statements above, we would know the following. Angle A is congruent to angle F. Side AB is congruent to side FG. Angle B is congruent to angle G. Side BC is congruent to GH. The segments and angles in each problem are corresponding parts of two congruent triangles. Make a sketch of the two triangles and mark congruent parts. Then identify the congruence pattern that justifies your statement. Finally, write a congruent statement for each pair of triangles represented. All right, so for question 1, we are told that side ML is congruent to side ZJ. We're also told that side LR is congruent to side JB, and we're told that angle L is congruent to angle J. All right. So our first task here is to do a sketch of these triangles. What's kind of nice about this problem is that as long as the triangles are congruent, they can really look like anything that we want, right? So we don't really need to worry too much about what the triangles look like as long as they basically look the same, right? So I'm just going to draw one triangle. And then I'm going to draw the same triangle, roughly. All right. And these are my two congruent triangles. So the first statement that we're given is that side ML is congruent to ZJ. So what that means is on the triangle on the left, I've got three vertices. I'm just going to pick two of them. One of them is going to be M, and one of them is going to be L. So I'm going to put an M up top, and I'll put an L on the left. And because I did that on the triangle on the right, I want Z to correspond to M, right? Because they're both in the same spot, essentially. And then I want J in my second triangle to correspond to L. Because again, those letters are in the same spot. And we are told that those two sides are congruent, and so the way I'm going to indicate that is by putting the same number of slashes in the side. So I'm going to have 1 and 1, just like that. So because they both have one slash in them, that visually tells us that those two sides are congruent. Second statement says that LR is congruent to JB. Well, I've already placed L, so I can't replace it. So I'm kind of locked into L being there. R, I have to place, but I only have one more place to put it. Right? There's only one more vertex that hasn't been labeled, which kind of has to be R. Likewise, on the right, we're talking about JB, so B kind of has to go there. And again, we're told that these two sides are congruent. So I want to indicate that LR is congruent to JB. Now I can't use one slash because I've already used that. And I have no information about how, say, ML relates to LR. So I cannot use one slash. So I'm just going to use 2. And 2, just like that. And then finally, for part A, we're told that angle L is congruent to angle J. So now, in order to indicate that my two angles are congruent, I'm just going to put a single curve at the angle for L and a single curve for the angle for J. And so that is it for part A. Part B is asking, all right, well, what is the congruence pattern that we have here? And just as a quick reminder, the various congruence patterns that we can choose from are side, 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 angle, side, angle, side, angle, and angle, angle, side. The last two are in some ways they're kind of sort of the same thing. We'll deal with that when we have to deal with it. It's not going to we're not going to encounter it with number one. With number one, in order to figure out which congruence pattern it is, we want to look at what parts of these triangles are congruent. Notice that for the triangle on the left, if I start at M and I sort of trace the parts that are congruent, if I start at M and I go like this, notice that I'm covering one of my congruent sides, then I hit my congruent angle, and then I hit my other congruent side. So in this situation, and then the same thing happens on the right, right? I'm tracing my congruent side, I hit my congruent angle, and then if I keep going, I hit the other congruent side. So what I have here is I have my congruent angle is between my congruent sides. And if you take a look at SAS, well, in this case, my angle, A, is between the two sides, S and S. So this congruence pattern is SAS. And although it's not part of this, oh no, it's the next part. So let's get on to C actually. So that's it for B, side angle side. For C, they're asking for the congruent statement. So this is now, because we have SAS, we know that these two triangles are congruent. They are identical. They have all of the same side lengths. They have all of the same angles. They have the same perimeter. They have the same area. These are the same triangle, just with different letters and in different spots. So all I need to say for C now is I need to say that the two triangles are congruent. Now, what you want to be careful here is whatever order of letters you choose for one triangle, you need to make sure that the corresponding order in the second triangle is the same. So what I mean by that is for the triangle on the left, I basically just have to pick some order for the three letters, M, L, and R. So I'm just going to write them in that order. I'm going to write them as M, L, and R. And that ordering is quote unquote random. And maybe when you did this problem, you used a different order for the first triangle, and that's okay, right? So there's nothing really special about the order M, L, R. That's what I chose to do. Now, that triangle is congruent to the triangle on the right. Now, here's where you're sort of locked into something. For me, because I went in the order M, L, R, I need to make sure that when I list the vertices for the triangle on the right, that it's in the same order that corresponds to each of those vertices. So I started with M, and M corresponds to Z, which means I have to start with Z in the other triangle because M corresponds to Z. Likewise, J corresponds to L. They're basically in like the same spot. And B corresponds to R. So once again, the order that you choose for the first triangle doesn't really matter, but then whatever you choose, that locks you into the ordering for the second triangle because you need to make sure that they correspond. And if you have a different answer for C, that's fine as long as each vertex corresponds between the left and the right. Question 2. We're told that side WB corresponds to side QR, side BP corresponds to side RS, and side WP is congruent to QS. Each pair here is congruent, not well. They also correspond, but specifically they are congruent. So We're going to do a sketch. And once again, it doesn't really matter what our triangles look like as long as they're congruent. So this time I guess I'll do an obtuse triangle just to mix it up a little bit. That's my first triangle. That's not perfect, but I think it's good enough for today. So these are my two triangles, and I have to label these. So the first statement that we are given is that WB is congruent to QR. So on the triangle on the left, I have to just choose a W. We'll just make it top left. And I have to choose where B is going to go. We'll go bottom left. And we are told that that is congruent to QR on the right. So I'm going to go in the same order. So Q is going to go top left. R is going to go bottom left. And we're told that these two sides are congruent, so I'm going to indicate that with a single slash, just like that. Our second statement says that side BP is congruent to side RS. Well, there's only one place where I can put P now, which is bottom right. And likewise, there's only one place I can put the S, which again is bottom right. And we're told that BP is congruent to RS, so I want to indicate that those sides are congruent. I can't do one hash mark because I've already done that, so I'm going to do two, just like that. Our third statement is that side WP, which is already labeled on the left, is congruent to side QS, which is also already labeled. So I just want to indicate that those are congruent, and this time I have to go with 3. Also, just to clarify, the number of slashes does not have anything to do with the length of the side by itself. So clearly in this picture, WP and QS, they are my longest side, but it was really just a coincidence that that had the most number of slashes. So just to clarify, the number of slashes does not indicate that it's larger or smaller than some other side. You're just using the slashes to sort of compare them with some other side in another triangle, or even in the same triangle. Part B is we are asked to identify which congruence pattern is this one. Well, with this one, notice that all we've done is we've talked about sides, and we haven't said anything about the angles. So this one, I think, is relatively straightforward because there's no A that we've even mentioned. So the congruence pattern is going to be side, 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 SSS. And again, what that tells us is that when you have side, 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 when you have the congruence pattern of side, 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 not only are the sides congruent, but also all of the angles are congruent, and all of the related measurements of these triangles are congruent. Perimeter, area, and anything else. These two triangles are congruent in every way. They just have different letters and they're in different spots. Part C asks us to identify or to write a congruent statement that relates these two triangles. And as we saw with number 1, the first part of your congruent statement, the order doesn't really matter. We have to just choose W, B, and P, and we have to write them in some order. So I'll just write them in that order, W, B, P. So we're going to say triangle W, B, P. All right, so that's the order that I'm going in for my first statement, which is quote-unquote random. I just went with any order I wanted to. But now, for the second part of this statement, I have to be careful that the order, I have to say what corresponds to W, what corresponds to B, and what corresponds to P in that order. So Q corresponds to W, R corresponds to B, S corresponds to P, and so the order that I'm going to say on the right now is QRS. So WBP is congruent to triangle QRS. Question number 3. So for 3, we are told that side CY is congruent to side RP. We're told that angle Y is congruent to angle P, and we're told that angle E is congruent to angle B. This time, maybe I'll go with like a quote-unquote upside down triangle. Again, whatever the triangle looks like, it doesn't matter too much, as long as each one's roughly the same, each sketch. All right. So these are my 2 triangles, and our first statement is that CY is congruent to RP. So on the left, I'll just say we'll make this C and we'll make this Y. So CY is on the left. Likewise, C corresponds to R, so R is going to go there, and Y corresponds to P, and so P is going to go there. And we want to indicate that those 2 sides are congruent to each other, so slash and slash. We're also told that angle Y, which we've already labeled, is congruent to angle P, which we've already labeled. So to indicate that angles Y and P are congruent, we'll just have a single curve at Y and a single curve at P. Our last statement here is that angle E, which we haven't labeled yet, is congruent to angle B, which we haven't labeled yet. There's only one place for E to go, and there's only one place for B to go. And we want to indicate that these angles are congruent. Well, we've already used one curve, so in order to indicate that E and B are congruent, we will use 2 curves, just like that. And that is all of the information that we're given. So now for B, we want to indicate what is our congruence pattern that we have here. So notice that we have 2 angles and a side, right? 2 angles and a side. And so, we can choose between the 2 statements. I wrote them back up here on the left. So of the 4 congruence statements, 2 of them involve 2 angles, this ASA and AAS. And those 2 conditions are they're kind of the same in some ways. So if you mix them up, it's not really the end of the world. The one that's, I guess, quote unquote, better to use for number 3, notice that in your picture, notice that the side that's congruent, so looking at the triangle on the left, we have CYE. Notice that the side that has the hash mark in it, CY, it is not between my 2 congruent angles, right? The side that's between my congruent angles would be YE, but instead the side that is congruent is CY, which is not between the 2 angles that are indicated as being congruent. So what that means is, and then this obviously the same thing is true for the triangle on the right. So what that means is our congruence pattern, it really should be angle, angle, side. Notice that when you look at AAS, the S is not between the 2 A's, right? And that's different from angle, side, angle. So we have angle, angle, side. Now, having said that, the other congruence condition, which is angle, side, angle, that actually follows from this. That follows from angle, angle, side, because really, if you know 2 angles of a triangle, you also know the 3rd angle, and so technically we also know that angle C is congruent to angle R, simply because you're kind of locked into those values. And if C is congruent to R, then you have angle, side, angle. So there isn't a large difference between AAS and ASA. But if you're looking for sort of like the best answer for 3, I would say it's angle, angle, side. But angle, side, angle is also not a bad choice, if that makes sense. But it's definitely not side, angle, side, or side, side, side. Those responses would in fact be incorrect. So our congruent statement here, the triangle on the left, I'm just going to pick a quote random order. We'll go CYE. It's not really random, it's just the order in which I labeled things, but it's fine. And then once I choose that order of CYE, I have to make sure that in the second part of this congruent statement that the letters on the right correspond in the same order to what I wrote on the left. So R corresponds to C, P corresponds to Y, and B corresponds to E. So I'm kind of locked into that second order once I choose my first order. Moving on to the set section. Now, the set section only has one question in it, but it's kind of a longer question, and there's a lot of sort of exposition before we get to the question. There's a decent amount, not only in the directions, but sort of like helping us through this problem. So I am going to read out everything that's here, and as we'll see, this description really does help us answer the question. So there's a lot of information that's presented here in the description. So let's get right into it. Olivia is studying triangle ABC and quadrilateral ADEG as shown in the figure. And we'll be doing a lot of back and forth here, but we've got our picture here. So we've got a triangle and we've got a quadrilateral in this picture. So, her teacher has told the class that quadrilateral ADEG is a rectangle. So it's a specific quadrilateral that we know is a rectangle, and that GE bisects both segments BC and AB. All right. The assignment is to prove that triangle BGE is congruent to triangle EDC in a 2-column proof. So, just to summarize, our Olivia's teacher has said that this quadrilateral is a rectangle. So we are allowed to treat that quadrilateral with any of the properties of rectangles that we are familiar with. And we are told that GE, which is this line segment right here, bisects both BC and BA. Okay? So, continuing on. Olivia starts to organize her thinking by writing what she knows and the reasons she knows it. All right. I know that GE, this guy, bisects BC and AB because I was given that information, right? Olivia's teacher told her that this is true. So if you think back to the first lesson in this unit, this would be an example of knowing something by authority, right? In this case, the teacher is considered an authority, and the teacher is telling Olivia that GE bisects BC and BA, and so Olivia and us and we know that that is true from authority. All right. Olivia also knows that BE, which is this piece right here, is congruent to EC, which is this piece right here, and BG, which is this piece right here, is congruent to AG, which is this piece right here, by the definition of bisecting. So bisecting means to essentially cut in half. And so because GE bisected both of those longer pieces, we know that BE is congruent to EC and BG is congruent to GA. Both of those longer sides got cut in half. Okay. Olivia also knows that AG, which is this piece right here, is congruent to DE, which is this piece right here, because they are opposite sides of a rectangle. Okay, well, we were given that that quadrilateral is a rectangle, and one of the properties of rectangles is that opposite sides are congruent. And so therefore AG is congruent to ED due to properties of a rectangle. And Olivia also knows that BG is congruent to, oh, sorry, that's not BG. BG up here is congruent to DE down here by the transitive property. And just to clarify, we were already told that BG is congruent to GA because they got that long side got bisected. And then due to the fact that they're both in a rectangle, they're both opposite sides of a rectangle, we were told that GA is congruent to DE. Right? So BG is the same thing as GA, and GA is the same thing as DE. Well, the transitive property tells us that if A is congruent to B and B is congruent to C, then A is congruent to C, which means that BG is congruent to DE. That's what that last bullet point is saying. So that's how the transitive property works. So A is congruent to B is congruent to C, therefore A is congruent to C. So Olivia knows all of those things. Now, hold on. All right. Olivia realizes that she already has two sets of corresponding sides that are congruent in triangle BG and EDC. So what that means, and let's go ahead and draw that picture. Notice that in the bullet points here, I'm gonna label everything that that she said. So she knows that BE, that piece, is congruent to EC, which is that piece, and she knows that BG, which is this piece, is congruent to AG, which is this piece, and AG is also congruent to DE, which is that piece right there. So what this is referring to is, notice that in the triangle up top and in the triangle in the bottom right, notice that we have two pairs of congruent sides, right? So that's what this piece is referring to here. Olivia realizes she already has two sets of corresponding sides that are congruent. Now, she only needs to prove that the third side's congruent to have side angle side, right? Because if you have three pairs of congruent sides, that is side, side, side. Or, right, as an alternative, maybe find some angles that are congruent, right? Because it's not, our side, side, side is not our only option. Maybe it's side, angle, side. Maybe it's angle, side, angle. Maybe it's angle, angle, side. In order to have a different congruence pattern. She wonders if the rectangle can tell her more about the two triangles. All right, well, Olivia also knows some things in this picture that her teacher didn't explicitly tell her, but she knows from before. I know that all of the angles in ADEG are right angles because ADEG is a rectangle. So ADEG, every single angle here is a right angle because that's basically the definition of a rectangle. The definition of a rectangle is that it's a quadrilateral with four equal angles. And because the sum of the angles of a quadrilateral is 360, the only way that that can be true is if each angle is 90 degrees, which is a right angle. So the definition of a rectangle is that it has 4 right angles. Olivia also knows that angle GAD, that's actually a typo, so we're going to go ahead and fix this. This should say angle AGE. All right. So Olivia knows that angles AGE and angles BGE are both right angles because they form a linear pair. So AGE we've already indicated, and BGE is right here. So that is also a right angle. Okay. Olivia also knows that angle ADE and angle CDE are both right angles because they form a linear pair. So ADE we've already indicated, and CDE is that angle right there. That's also a right angle. All right. Now, finally getting to question 5. Olivia is excited to have 2 sides and an angle. So looking at both of these triangles, both triangles in this picture, that is BGE and EDC, they've got 2 pairs of congruent sides and 1 pair of congruent angles. But she quickly notices that she has side-side angle. No good. And she knows that is a pattern she can't depend on. When you have side-side angle, if you want to reverse it, that's your call. No matter how you write it, it doesn't work, right? Side-side angle is not a congruence condition for triangles. In other words, what that means is if you have side-side angle, it's possible that the triangles are congruent. That's certainly possible, but you don't know it for certain. So we cannot depend on it. But right triangles are special because if you have 2 sides, of any right triangle, the third side can be found by doing the Pythagorean theorem, right? So our angle in each of the triangles here is a right angle, and so even though we can't really use that as an angle in our congruent statement, not yet at least, because as a right angle, it does tell us that we're dealing with a right triangle, and right triangles have some unique properties that we can use. Olivia believes she has her proof idea and begins to write her proof using as many mathematical abbreviations or symbols as she can. Help Olivia finish her proof. So, our proof starts like this. We are given that quadrilateral ADEG is a rectangle, and we are also told that ED bisects BC and AB. So ED bisects both BC and AB, and we want to prove that triangle BGE is congruent to triangle EDC. All right. So, our 2-column proof looks like this, and we've already started by writing out some statements and writing out the reason that we are able to say that statement. So, the first statement is that quadrilateral ADEG is a rectangle. That is a true statement, and the reason that we are able to say that is that we were given that information. Okay. Statement number 2. GE bisects BC and AB. They wrote it this time, which is nice. And the reason that we were able to say that is that that is given. Now, notice that if you go back to Olivia's thinking here, pay attention to these bullet points here. So we've already incorporated this piece of information, right? I know GE bisects BC and AB because I was given that information. Well, okay, that's already appeared in our proof, right? We were given that. And then notice that the second bullet point comes from the first bullet point, right? So given that GE bisects both of those things, it tells us that we've got some line segments that are congruent. Well, this is a handy thing to know, and this is a handy thing to know. And they follow from the fact that we have a bisector here. So in order to construct our proof, we want to include those statements, right? And this is what I meant earlier when I said that all of the exposition kind of helps us fill in this proof. For statement number 3, we can say that BE is congruent to EC, which, I mean, we already said this, right? It's right there. It's this statement that's already in the description. But the idea here is that we have to include it in our proof. We have to say that BE is congruent to EC, just like in Olivia's notes. Now we are working it into our formal proof here. But we have to give a reason, and this is a key component of proofs like this, is that you have to back up everything you say with some sort of a reason. Now, the reason that we can say this is that this is simply the definition of what it means to be a bisector. When you bisect something, it cuts it in half. And so from statement 2, GE bisects BC, all right, well, that means it cuts it in half. So that's why we can say each piece is congruent to each other. Likewise, for statement 4, we can say that BG is congruent to AG. We already said this in the notes. It is right there. So we just have to make sure that we include that idea in our 2-column proof. We have to be able to back up everything we say on the left. And the reason that we can say this is, once again, this just follows from the definition of a bisector. When you bisect something, you cut it in half, so each of the pieces are congruent to each other, so therefore BG is congruent to AG. Now, what's another thing that was said? Well, notice that, all right, so we've sort of we've now used up that bullet point. The third bullet point here says that Olivia knows that AG is congruent to DE because they are opposite sides of a rectangle. Notice that in our proof, statement number 1 already established that we're dealing with a rectangle, right? So from statement 1, we can now also say statement 5, which is AG is congruent to DE, just like we said earlier. And we have to be able to back that up somehow. And the way that we can back that up is by saying that we know that opposite sides of a rectangle are congruent. That is one of the properties of rectangles that is firmly established. So because quadrilateral ADEG is a rectangle, which we established in statement number 1, we are allowed to say statement 5, AG is congruent to DE, because we know that opposite sides of a rectangle are congruent. Okay, statement 6. Again, going back to Olivia's notes. How nice that Olivia did a lot of the heavy lifting for us. So we've used up that third bullet point. The fourth bullet point says, I know that BG is congruent to DE by the transitive property. So, where did we write the transitive? Oh, no, I guess I erased it. But you might remember earlier we talked about how the transitive property works. We don't have to. We can just say this now. So for statement 6, we know that BG. Oh, do it in black. BG is congruent to DE. And you can see it in the proof too, because BG is there, which is congruent to AG, and AG is congruent to DE. So that means that these two things have to be congruent because both of them are congruent to the same thing. And again, the transitive property says if A is congruent to B and B is congruent to C, then A is congruent to C. So we are allowed to say this, and our reason is simply the transitive property. Which has been firmly established. Transitive property is true. All right. So that sort of uses up all of the bullet points there. And then Olivia's thinking, and then we come to this bullet point. Olivia knows that all of the angles in ADGE are right angles because ADEG is a rectangle. Well, that seems like that's going to be some useful information here. So for statement 7, we know that a whole bunch of angles are congruent to each other. So all of the angles inside the rectangle are congruent to every other angle inside the rectangle because they are all right angles. So we're going to have a lot of letters here, so just bear with me. So the angles of the rectangle are EGA, which is congruent to angle GAD, which is congruent to angle ADE, which is also congruent to angle DEG. All I've done here is I've just listed all 4 angles inside the rectangle. All right? And we're able to say that all of them are congruent to each other because of the definition of a rectangle. And also right angles. Honestly, I think if you just said the definition of a rectangle, I think that would be sufficient. But yeah, so all of the angles of a rectangle are congruent to each other. All right. Again, going back to the notes. So we've accounted for that bullet point. Olivia was also able to say that I know that angle AGE and BGE are both right angles because they form a linear pair. Well, let's throw that in there. So for statement 8, actually for statement 8, we're gonna mention both pairs of linear angles. So we're going to say that angle BGE is congruent to angle AGE and angle ADE is congruent to angle CDE, which Olivia already talked about. And the reason that we're able to say that is the definition of linear pairs and both are 90 degrees. So if you have a linear pair of angles and they are 90 degrees, then each one is congruent to every other one. All right. So for statement 9, at this point, the notes start to peter out a little bit because we've covered this and we've covered this. So we're not done yet, but we're sort of out of bullet points. But notice this piece right here. If you have two sides of any right triangle, the third side can be found by doing the Pythagorean theorem. And that's going to be sort of like the last piece that sort of unlocks this problem for us. And then the rest of it will be somewhat straight. The last step will be somewhat straightforward. So what that means is, if I take a look at my picture, which is all the way back up here, so we don't really know anything about that side there yet. We don't know anything about GE. But what we do know is that the Pythagorean theorem says if we take BG and square that, and if we add GE and square that, we're going to get BE squared. Right? That's what the Pythagorean theorem says. Likewise, in the bottom right, we know that ED squared plus DC squared is going to equal EC squared. Well, if I take my first equation, all right, if I take my first equation and if I solve for GE, what's going to happen is this BG, it's going to come over to the right, okay, just like that, and we are going to get this equation right there. Okay, that just follows from the Pythagorean theorem. So what I'm going to do is I'm actually going to go ahead and write that. So for statement number 9, we know that if we take B, come on. There we go. If we take BE squared, which was the hypotenuse squared, and if we subtract BG squared, we are going to get GE squared. And we know that from the Pythagorean theorem. Likewise, I'm not going to scroll back up, but it's the same general idea. For number 10, we can do the same exact thing for the triangle in the bottom right. And if we solve the Pythagorean theorem for our missing side, we will find out that EC squared, which is the hypotenuse squared, if we subtract one of the legs, specifically if we subtract DE squared, we will get the other leg squared, which in this case was DC. And we know that from the Pythagorean theorem. Okay? Now, notice that we've already established that BE and EC are the same thing. We've established that those two are the same. We have also established that BG and DE are the same thing. Okay? So because all of those are the same, if you sort of take 9 and 10 and sort of look at them together, Well, if BE is the same thing as EC, and if BG is the same thing as DE, then what that means is GE squared has to be the same thing as DC squared, right? Because everything that goes into those equations is the same, so therefore the result has to also be the same, and that's just substitution. That's algebra. That's not even geometry. That's just saying, all right, we'll just manipulate my equations. So GE squared is the same thing as DC squared. What's nice about that Sorry about that. What's nice about that is that if you take a look at our picture, well, if GE squared is the same thing as DC squared, it means that this has to be the same as this. Right? Those two side lengths have to be the same, because when you square them, you get the same number. So now we've established that we have 3 pairs of congruent sides between these two triangles. So therefore, for statement number 12, we can write our conclusion, which is that BGE, that triangle, is congruent to triangle EDC, because we have established that we have the congruence condition of side, side, side. And so that is the completion of our proof from start to finish. Moving on to the Go section. The Go section also has one question in it, just like the Set section, and also like the Set section, the one question in Go has multiple parts to it, but let's just sort of take it one piece at a time and just perform each of these transformations, and we'll take it from there. So, directions for 6 say, perform the following transformations on triangle ABC. Use a straight edge to connect the corresponding points with a line segment. Answer the questions. So, part A, reflect triangle ABC over line LK. Label your new image triangle A prime, B prime, C prime. All right, so, looking at our picture here, so we've got a triangle in quadrant 2, and the first part of this problem is asking us to reflect that triangle over LK. Now, this is not the easiest reflection to do, and the reason is because the slope of line LK is not very pretty. Okay? So if you want the slope of LK, well, they give you point L, they give you point K. Going from L to K, it actually turns out we go down 7 and we go to the right 3. So the slope of LK, which again is our line of reflection, going from L, 1, 2, 3, 4, 5, 6, 7, and we go to the right, 1, 2, 3. So line LK has a slope of negative 7/3, which is, I mean, it's fine, but it's not a very pretty slope. It's not like 2 or 1/2, right? It's kind of an interesting slope to use in this context. And we have to reflect over it. And so in order to reflect any of these points, A, B, and C, each of these vertices, in order to reflect them over the line LK, we need to look at what is the slope. We'll call it M prime. What is the slope of the line that would be perpendicular to LK? All right, so what is the slope that is perpendicular to our line of reflection? And we know that when we're dealing with perpendicular slopes, what we want is we want the negative reciprocal. Okay, so the negative of a negative is a positive, so our slope is going to be positive, and the reciprocal of 7/3 is 3/7. So that is going to be the slope of the line that is going to connect each of our original points with its image after we reflect over this line of LK. So let's go ahead and sketch each of these lines from A, B, and C with a slope of 3/7. So we'll start with A. So from A, if I want a line that is a slope of 3/7, from A, it means I'm going to go to the right 7. So 1, 2, 3, 4, 5, 6, 7, and up 3. 1, 2, 3. So that puts me right there. Now, to be clear, that is not my point of reflection, right? That is not A prime. That point is just going to allow me to establish what is my line of reflection. So from A, I'm going to go to that point that I just drew, right? And we'll extend it a little bit, right? We'll just stop like there, I guess. Now, in order to identify, now I'm going to get rid of that red point because it's a little distracting. I knew that was going to happen. All right, we'll keep it until we're done, then I'll deal with it. So our point of reflection, in this case A prime, is going to be on that green line. That's why we drew it. So our point is somewhere on that green line. And in order to figure out where it goes, we need to recognize that this point of A prime, which is going to be somewhere on the green line, it is going to be an equal distance away from line LK as our original point A was from LK. So what that means is we need to start at A, and we need to look at, all right, well, how far do we go before we intersect line LK? So from A, if I go over, and I guess I'll do this in red, I guess. Actually, no, we'll do it in purple. I'll use more colors this time. So from A, I want to get to my point of intersection, which is right there, right? I want to figure out how far do I go from A to get to that point of intersection right there. So from A, I'm going to go over one. Oops, of course, that's still on that. Okay. I'm going to go over 1, 2, 3, 4, and like maybe some change. I don't know, maybe like a little bit more. It's hard to tell. And then I'm going to go up 1 and like almost 2. And again, this is all because of the slope of negative 7/3. That's what makes this a little bit more challenging because we're dealing with fractional boxes here, but we're just going to do the best we can. So we go to the right 4 and some change, and we go up almost 2. So what that means is from this point of intersection, I'm going to do the same thing. I'm going to go to the right 1, 2, 3, 4, and some change. And I'm going to go up mostly 2. So like 1 and then maybe like there, we'll say. So when all is said and done, my reflection point is going to be right there. And I'm going to get rid of all this extra stuff because we don't need it anymore. All right. So that point right there is A prime. Okay. We're going to do the same thing for B. So for B, remember, we want a line from B that has a slope of 3/7. So go ahead and do that. So from B, we're going to go over 1, 2, 3, 4, 5, 6, 7, and up 3. And that's, I did not want that to be a straight line. We'll do that again. So 1, 2, 3, 4, 5, 6, 7. And then I'm going to go up 3. So 1, 2, 3. So that establishes that my perpendicular line is going to go through that point right there. So let's go ahead and draw that line. So from B, all right, that's our line, and we'll extend it just in case we have to. All right, I will get rid of the purple. We no longer need it. All right, so to get B prime, I know it's somewhere on that red line. And in terms of where it's going to be on that red line, I know that that wherever it is, it's going to be the same distance from LK as my original point B was from LK. So that means I'm going to go back to B, my original point here, and I'm going to see, all right, well, how far or how long does it take me to get to that point right there? How far is it from B to my point of intersection with LK? So do this in purple. So I'm going to go over 1. That's the second time I've done that. I'm going to go over 1, 2, 3, 4, and like mostly 5. So it's almost 5. And then I'm going to go up 1, 2, and maybe a tiny bit more than that. So it's almost 5 and then a little bit more than 2. So let's do that again. So from here, we're going to go over 1, 2, 3, 4, 5-ish. And then 2 and maybe a little bit more. So 1, 2 brings us to right there. And so when all is said and done, my reflected point for B is going to be right there. I'm going to get rid of all this extra stuff. I no longer need it. Okay. And that point is B prime. B prime. All right. C. Again, from C, we are looking for a point. We're looking for a line with a slope of 3/7 from point C. So from C, I'll go over 1, 2, 3, 4, 5, 6, 7, up 3, 1, 2, 3. And so we are looking for a line that goes through that point. So we're looking for that line. And I know that C prime is going to be on that line, and it's going to be the same distance from C to LK is going to be the same distance from LK to C prime. It's going to be somewhere on that purple line. So we want to figure out, okay, well, how far is it from C to that red dot? What's the path, essentially? So it looks to me like we go over 1 and then some change, maybe a half, maybe a third, something like that. And then we're going to go up like not even a full box, maybe like 2/3 of a box. Right? So let's do the same thing. So we're going to go over 1 and maybe a little bit more. And we're going to go up not quite a full box. So that brings us to there. And so our reflected point C prime is going to be right there. I'm going to clear out the rest of my stuff here because we don't need it. And I just erased my point, but luckily I remember where it was. It was right there. And that point is C prime. And we lost our A from earlier, A prime. And if I connect my points here, A prime to B prime, B prime to C prime, and C prime to A prime. And that is my triangle reflected over LK. And we have answered part A. And again, the reason why that took us so long is because of the slope of this line. This is not an easy line of reflection to do. Negative 7/3 is not it's not very straightforward at all. But we got through it, and let's keep going. All right, I'm not going to scroll up, but I am just going to read it out. 6b says, what do you notice about the line segments A prime, B prime, and C prime? So for B, well, A prime is that line right there. B prime is that line right there. And C prime is that line right there. And we kind of already knew this because this is how we created this figure. But for part B, we can tell that all of these lines are perpendicular to our line of reflection, LK. Right? We sort of already knew that, but now that you see our picture, you know, it's been cleaned up a little bit, it's pretty obvious that all of those lines are, in fact, perpendicular. All right. Part C. Compare line segments AB, BC, and CA. So all of the different line segments in the original triangle. Compare those to A prime, B prime, B prime, C prime, and C prime, A prime. So in other words, compare them to all of the line segments in our new triangle. What is the same and what is different about these segments? So for part C, what they have, the way that they are the same is that they are congruent. So AB is congruent to A prime, B prime. BC is congruent to B prime, C prime. And CA is congruent to C prime, A prime. Those side lengths are the same between the original figure and the image. But they have different slopes. Okay. So they are congruent, but they have different slopes. And I realize maybe I should be typing this instead of writing it, but it's legible, and I think for this problem, I think we're just going to stick with writing it. Part D. Translate triangle ABC. That's the original triangle. Translate ABC down 8 units and right 10 units. Label your new image A double prime, B double prime, C double prime. The formatting's a little off on that question, but that's fine. So we're going to go down 8 and to the right 10. All right, this is going to be easier than the reflection. This is not going to take us nearly as much time. So for part A, or sorry, for vertex A, we're going to go down 8 and to the right 10. All right, so that means we're going to go down 8. So 1, 2, 3, 4, 5, 6, 7. That brings us to there. And then to the right 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right there. We'll do a bigger dot just so we don't lose track of it. So that is right there. And that is going to be A prime, or sorry, A double prime. Double prime. Okay, we're going to do the same thing with B. For B, we're going to go down 8. So 1, 2, 3, 4, 5, 6, 7, 8 brings us to there. And then to the right 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're on the y-axis. So that's right there. And that is B double prime. Do the same thing with C. Go down 8. 1, 2, 3, 4, 5, 6, 7, 8 brings us to there. And to the right 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 brings us to right there. And we can go ahead and connect these. So this is C double prime. So A double prime to B double prime is right there. B double prime to C double prime is right there. And C double prime to A double prime is right there. And that is everything for D. So the translation was significantly easier than our reflection, which is nice. For part E, what do you notice about the line segments A? So A double prime, B double prime, and C double prime. So what happens when we connect our image to our pre-image? I guess we'll use maybe green. Try that. So A to A double prime looks like that. B to B double prime looks like that. And C to C double prime looks like that. Well, what do we notice? Well, they're all parallel. Those green lines are never going to intersect. They've all, each point's been shifted the same amount. So the slope is the same, and if the slope is the same, that means that they are parallel. So for E, we can simply say that they are parallel to each other. Okay, nice. F. Part F, compare line segments AB, BC, and CA. So all of the side lengths of the original triangle to A double prime, B double prime, B double prime, C double prime, and C double prime, A double prime. Those are the side lengths of the translated triangle in quadrant 4, bottom right. What is the same and what is different about these segments? Well, again, just like C, they are congruent. So the size of the triangle did not change. The side lengths did not change, but they are in different spots. Right? The orientation of the triangle is the same, and it's the same size. It's just it moved from quadrant 2 to quadrant 4. That's all. Other than that, it's basically the same triangle. Part G, translate triangle ABC. So again, we're going back to the original triangle. Translate triangle ABC down 10 units and reflect it over the y-axis. Label your new image with triple prime. Okay, so we're going to have a reflection here, but luckily this reflection is going to, again, be significantly easier than what we did in part A. So we're going to go down 10 and then reflect it over the y-axis. So let's take each point here. We'll start with A. So from A, I'm going to go down 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That brings us to there. Now, I'm going to reflect it over the y-axis, and the reason why this is going to be significantly easier than how we started this problem is that it's just a straight shot to the right. Okay? I'm going to the y-axis. So if I'm going to count to the y-axis, we'll do this in, I guess, purple. So if I'm going to count to the y-axis, let's count 1, 2, 3, 4, 5, 6, 7, 8. Well, that makes sense because the x-coordinate there is -8, which means it's going to take me 8 units to get to the y-axis, which means if I go another 8, 1, 2, 3, 4, 5, 6, 7, 8, that brings me to right there, and that is where my translated and reflected point is going to go. It's going to go right there. And that point is A triple prime. All right. Get rid of that. We don't need it. Get rid of that. Get rid of that. We'll do the same thing with B. With B, we are going to go down 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That brings us to here. Notice that our x-coordinate is negative 10. Right? We're right. We are right there. Yeah, we're right there. Notice that our x-coordinate is negative 10, which means when we flip it over the y-axis, we're going to go 10 and then 10 more. Well, we don't really need to count all that because we kind of know where we're going to end up. We're going to end up right there. Right? We're going to go from negative 10 to positive 10. So that point is B triple prime. Right. And then we're going to do the same thing for C. For C, we're going to go down 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That brings us to there. So right there. And our x-coordinate is negative 5, which means we're going to go 5 and then 5 more. Well, that's going to bring us to positive 5, which is right there. Okay. Let me move this C double prime so it's out of the way. So that point there is still C double prime. This point that we just did is C triple prime. And now I'm just going to connect my points here. So A to B, B to C, and C to A. Get rid of my purple guy. That is G. What do you notice about the line segments? All right, it's the same thing. So A to A triple prime. All right, we'll, I guess, use purple this time. And go with there. So A to A triple prime. All right, this is going to overlap with a whole bunch of stuff, so it's going to look a little crazy, but we're almost done. So A to A triple prime, B to B triple prime, and C to C triple prime. Oof. So what do we notice about these? Well, there's not really a whole lot to say about the purple lines. I'm not really seeing much that we can honestly say that's like super valuable here. The only thing I can see here is that they intersect, which the other ones didn't do. So notice that when we did a reflection, the red lines don't intersect. When we did a translation, the green lines didn't intersect. But when we did both, when we did a translation and a reflection, notice that all my purple stuff sort of overlaps and it gets kind of messy. So for G, it's just that they intersect, which didn't happen before. And then finally for part I, compare the sides of my original triangle to the sides of my latest triangle with the 3 primes. What is the same and what is different about these segments? Well, similarly to part C, I'm noticing that, so this is, this is part, this was not G, this was H. So that's H, and now we're answering part I. So similar to part C, the sides of the triangle are congruent. They're not bigger or smaller. They're the same length. But again, just like in part C, but they have different slopes. And that is how the sides of my new triangle compared to the sides of my original triangle. And we are done what is kind of a monster problem, but we got through it. So that's everything with question number 6.